just to start, I will tell you a few words about what we mean by what is topological, very roughly, what is topological data analysis. In fact, topological data analysis started as a field known as topological data analysis about 25 years ago. And it started from the very basic observation that when you look at data in general, this data seems to carry some kind of structure, topological structure. And I'm just going to show you a few examples here, very simple to give you an idea what we mean. So, for example, if data can come in general as, in some many cases, it can just be a discrete set of observation of samples. For example, here you have an example where you see a 2D projection of a point cloud in some high-dimensional space. And when you get data sampled in a possibly high-dimensional space, in general, this data is not sampled uniformly in the space, but it is often concentrated around some kind of structures that have some kind of geometry or topology. And when you do topological data analysis, what you want to do is to try to characterize this structure and to get some information about the topology of this structure. For example, here, this point cloud is coming from some application in cytometry. And what people want to do is to be able to segment, clusterize this data in such a way, each point represents a cell in a blood sample. And people want to distinguish different group of cells. Ultimately, the ultimate goal being to identify some cells that are characterized from some kind of disease. Okay? So this is a very first idea that you have a point cloud in some possibly high-dimensional space. This point cloud is sampled around some kind of topological structure, and you want to get some tools and some mathematical and algorithmic tools to be able to characterize and to say something about this underlying structure. Another example where you can see topology in data is when the data point, or each observation in your data set is itself already quite complex object. For example, here you have an example of a 3D image. So this is a cube, and inside the cube you have some voxels. It's like pixels, but in 3D. And the color of this pixel tells you if you are gray, you are in the this is a small piece of a porous media, a porous rock. And depending on the color of the pixel, you are inside the matter or you are in a void. And so this is not the whole data set. This is just one sample in my data set. But this data is already a complex object that in itself carries some topology. For example, you might be interested in understanding the geometry or the topology of the void because it is probably correlated to the, for example, the permeability of the rock or something like that. Okay? So there are two cases. Some cases where you have a whole data set that is represented as a discrete set in some high-dimensional space or metric space, and you want to understand the global structure of your data set. And there are some other cases where you have a data set and each data point is itself a complex object. Same idea here. If you have a data set which is made of multivariate time series, when you have a multivariate time series like this one, for example, which is just representing the 3 coordinates of the acceleration of a sensor, it can be seen as a point cloud or as a trajectory in some Euclidean space, here in the 3D Euclidean space. And you can easily imagine that depending on what the sensor is, how the sensor is moving, you will have some kind of characteristic structure on this trajectory of the acceleration. Okay? Just to give you a few examples and an idea. And the general goal of topological data analysis is to provide mathematical tools and a practical method to be able to give sense of what we mean by having some topology. Because in general, you have a discrete set, just a data set, and it's not completely clear what we mean by the underlying topology or the underlying geometry of a data set. So what we want to try is to get some tools to formalize what we mean and to characterize this topology. And in the second step, which will be, we will talk about this first step, and we will talk about a specific central theory in this domain, which is called persistent homology during today. And tomorrow and on Thursday, we will talk about the second goal of topological data analysis, which is to take advantage of this topological information and data to do some further analysis, like machine learning or statistical stuff. Okay, so let's start now with to work with TDA. So TDA has known many developments in the recent years. So there is not a canonical way to do TDA, but I will start with some kind of global picture, which is the kind of standard or classical way to do TDA. So in general, at the beginning, what you have is some data. So you can think of let's think that we have a point cloud in some Euclidean space, finite point cloud, a discrete set in an Euclidean space, or more generally in a metric space. It is not necessarily in a Euclidean space. And when you have a finite set of observation, a data set, this is just a finite set, and in itself, it does not carry any topological information, right? This is just a discrete set. So in general, if you want, for example, here, when you look at this data set, which is a two-dimensional data set, it's just a finite set of points, if you look at it. And you can tell much more about its topology. But when you look at it with your eyes, you would probably tell me that, in fact, this data set is sampled around some circle or maybe some annulus or some kind of circular structure, right? And if we want to highlight this structure, what we need to do to be able to do some topology from a discrete set, we need, in some sense, to build some topological space on top of this data set. So a very naive or simple idea, if you want to start to do some topology, is to connect points that are close to each other. So you decide, for each point, you decide who are the neighbors of your given point. And in this way, you do what people in data science call a neighboring graph. For example, you can decide to connect all the points that are distant, less than some threshold, or you can decide to connect all the points, each point to its closest k nearest neighbors, etc., etc. Okay? And if you do that, you get a graph. But as we want to do topology, when you get a graph, you start to get a topological space, because the graph is a topological space, that will tell you something about the connectivity of your underlying set, but not much more. And if you want to get more in topological information, what we do, we also had, for example, the idea is that when 3 points are close to each other, we can also add to this structure a triangle. And if you have 4 points close to each other, you can add a tetrahedra, etc. Okay? And in this way, we build what is called a simplicial complex, right? If you are not familiar with the notion of simplicial complex, I will just recall the definition we will use in the following in a few minutes. But you can also think about just graph, neighboring graph. You had edges to connect the dot, you add triangle, tetrahedra, etc. And in this way, you build an abstract topological space that will reflect the structure of your underlying data. The problem is that when you do that, if you do it if you choose, for example, just one threshold and you say, I'm going to connect all the points that are at distance less than this threshold, you have to choose this threshold. And you can easily imagine that even in this case, depending on the threshold you choose, you might see very different topology for your topological space, right? Because at some point, maybe you will connect the 3 edges of a triangle, but not put the triangle, and this will create a small hole in your space, and this kind of things. So a very important and central idea when you do TDA is not to look at a given scale at which you connect the dots, but to look at all the scales at the same time. So now if you change your threshold and you increase the threshold, you build a family of graphs or simplicial complexes that is growing when you increase the size of the threshold. And the idea when you do TDA or what is called now persistent homology is not to look at your data at one given scale, to build one space at a given scale, but to look at a whole family of nested spaces and representing your data at different scales, and then encode the topology or the evolution of the topology of this growing family of spaces as your scale parameter increase, right? And for this, there is a theory which is called persistent homology that allows to encode this information in the form of what we call a persistent diagram. I will come back on all these notions in a moment, which is just a set of points in the plane, where each point represents some kind of topological feature that appear at some point in the. So this family of nested spaces is called a filtration, and each point can be interpreted as a feature appearing at some point in this family, a topological feature, and disappearing later. Okay? Okay, so that's persistent homology, and that's what we are going to talk about today. And what we were going to talk, and as you can see, the way we get the topological information in the form of a diagram, a set of points in the plane, which is in fact not very well suited to do statistical analysis or to do machine learning, because you can see it as some kind of feature or, of your data, associated to your data. But in general, when you do machine learning or kind of things, what you need as input for your features are vectors. Objects living in vector spaces. And the point here is that these persistent diagrams do not live in vector spaces. So there is a whole activity, which is a very active research area, where people develop some method to linearize persistence information in such a way that it can be processed in machine learning algorithm, etc. Okay, so we will talk about this second part probably tomorrow on the day, on Thursday morning. Any question? Is that more or less clear? Okay, so now I'm going to start to introduce a little bit persistent homology, but I'm not going to do it formally because it would take a little bit of time, and probably Thomas will talk about it in a more algebraic way. I will try to do it on a few examples, and we are going for a moment, to forget about this example of point cloud. What I told you is that, in fact, persistent homology is defined as soon as you have a growing family of spaces, topological spaces, and when you want to study the evolution of the topology of this growing family of spaces. So we will start with persistent homology for functions. So the family of spaces, growing family of spaces we are going to consider here on a few examples are the family of the sublevel set of real valued functions defined on a topological space. Just a few words about the history of persistent homology, very short history. The way it was formalized at persistent homology, it was done about 20 years ago, more by Herbert Erdelder group in Duke and Gunnar Carlson at Stanford. But in fact, there was some kind of prehistoric version of persistent homology that were already existing since the 90s, the previous century. In particular, some work by the group of Patrizio Frosini in Italia, and some work in more fundamental math by Baranikov at the beginning of the 80s too. And in fact, persistent homology has known many mathematical and practical developments since this period in many directions. I won't have, maybe Thomas will talk about different things, but there are lot of ramifications and things around about persistent homology now, and it's almost a whole field in itself. Okay, so let's start with a very simple example to try to explain you what is persistent homology. So I will start with this function. So this is a real valued function defined on a topological space X, which is just a segment, real segment. And as a growing family of spaces, I'm going to look at the sublevel set of my function. So here it's very easy because the sublevel set will be intervals. And the only topological information I have in the sublevel set is the number of connected components, the number of intervals, okay? So what I do when I do persistent homology, I do the following. I start from the far bottom, below the minimum of the function, and I look at how evolves the topology of the sublevel set when I increase my level here, I call it alpha, okay? So when I'm below this value here, Nothing happens. The sublevel set is empty, so there is nothing to tell. Something happened when I reach the global minimum of my function. And what's changed in the topology of the level set is that I go from empty sublevel set to one point in the sublevel set, so one connected component. So when I'm doing persistent homology, what I'm going to do is I'm going to record the birth of this connected component in my filtration, and I'm going to monitor it through the filtration. So I continue to grow my threshold, my level, and as you can see here, when I increase a little bit the level, my point will become a segment, but from a topological point of view, it remains just a single, it's still a single component, connected component, and I just monitor how it evolves. And then nothing changed at this level, but something will change again when I reach this level here for the function, where I reach now another local minimum that will create a new connected component. So again, I record the birth of this connected component, and I'm going to monitor this connected component. At the same time, I continue to monitoring the evolution of this one. So I increase again a little bit my level, and nothing happened. My two component grows until I reach this new local minimum, where a new connected component appear, right? And again, I record the birth of this connected component. And nothing changed until I reach now this point, which is this level, which corresponds to local maximum. And here, there is something different that happened, which is not the birth of a new component, but in fact, this component that was born here and this one that was born here just suddenly merge together, and they just become one. So my number of components decrease, and one of the two components disappear, being merged into another one. And the rule we apply when we are doing persistence is that we merge the most recently created component into the older one. So what we decide here, from the point of view of the lifespan, is that this component that was born here and die at this time. You can also imagine that you are filling the graph of your function with water, and you look at the lakes, and then you decide that when you reach this level, the lake which is still alive is the one that is the deepest one, okay? So here, this connected component that was born here die when it merged into the older one. And if I continue to increase my threshold, when I reach this second now maximum, which is a global maximum, the connected component that was born here get merged into this big one, the other one. And as this one is younger than this one, this is this one that dies. And at the very end of the filtration, what I get is that all the connected components are dead, except one, the one that corresponds to the global minimum, that persists forever. Okay? And at the end of the process, what do I have? I have a set of intervals, right? Where each interval represents the lifespan of a connected component across the filtration. Is that clear? Okay, and this object, this set of interval, is what is called a persistence barcode. And depending on where you are from or of your culture, you may represent this barcode also as what is called a persistent diagram, which is just a set of points in the plane, which is a completely equivalent representation, where you say that when you have an interval starting at level alpha, ending at level beta, you can just represent it as a point with coordinate alpha beta. Okay? Birth date alpha, death date beta, right? Intuitively, when you do TDA, which is just a first intuition, is that the longer is an interval, the more relevant is a topological feature, because this is some topological feature that you see for a longer time across your filtration, right? And when an interval is very small, or a point is very close to the diagonal, it corresponds to a feature that you see only on a small range of values of your interval, and it might be, and we will see why in a few minutes, it might be interpreted as some kind of topological noise. Yes?
So why did you say that the interval starting at alpha and at theta and vice versa are the first connected coordinates?
Because that's my rule. Now, there are some deeper reasons, but this is the rule we impose for persistent homology, that we always kill the youngest people. It's completely immoral, but the most recently created topological feature are the first. When there is a 2 mix, you kill the youngest one. The older I am, the more I like this rule. Okay, is that clear? And in fact, we need to do that to get all the nice properties of persistence. Okay, so that's the first example, where a very simple example, because here the only topological information we have in the sublevel set is connectedness. Now we are going to see another example, a little bit more complicated example. And what we are going to look at now is that we are going to consider this set of points, finite set of points in a plane. We are in R2, and we just take a function that goes from R2 to R, which is just to each point associate the distance to this point cloud, the distance to the closest point in the point cloud. Okay, so this is the distance function associated to this point cloud. And again, I can look at the sublevel set of this function. So the sublevel sets of this function are balls, okay, balls centered around my data points, okay. And I can look, as I did before, the evolution of the connected component. So I am not going to represent it here, because this is exactly the same gain as previously. At the very beginning, we have as many connected components as we have points. And then when we grow the ball, some balls start to intersect, and then some connected components disappear, etc. Okay? But but something here different also happen is that at some point, when you grow the ball, and you look at the union of this ball, which is the sublevel set of, you start to see some holes or some cycles in your sublevel set. And when you do persistent homology, you also want to keep track of this kind of topological change, appearance or disappearance of holes or cycles. And the way this is, so here, for example, at this stage here, at this level, you don't have any cycle, but at some point, you get some cycles that I created here, and you have as many as you have. These point clouds are sampled of B later. And exactly as we did with connected component, we monitor we look at the birth of these cycles, and we also look at when these cycles disappear. In practice, when they are filled here, okay? And in exactly the same way, and here, if you will look at this level, we see that all these holes that were before are dead. So this was the end of their corresponding persistent interval. But there are still a few cycles remaining here that have appeared quite late, and they are all encoded here in this barcode. So with one-dimensional topological features that are one cycles or holes, if you want, we do exactly the same job. The small problem here is that the intuition here is a little bit less clear, because with connected component, it was completely clear. You have some kind of canonical representative of a connected component, which is a connected component in itself. When we are talking about cycles or holes, it's not always completely clear, or there is not a canonical way to associate to a whole one canonical cycle. Here, it's very simple, but you can easily imagine some example where it's not completely clear. And the way to formalize this notion of holes and cycles of dimension 1 is through homology. Okay, so and just before telling you a few words about homology, I just want to mention that in the same way as previously, you can convert your persistent diagram. So this persistent diagram is just for one hole, or for one homology, and as this barcode into a diagram. You just have to take care about one small thing. This is just, I take the opportunity to do the remark. When you are working with persistent diagram, here, as you have a lot of symmetries in your data set, you have several times the same intervals. So when you convert an interval into a point, you have to think that this point may have some multiplicity corresponding to the number of times the interval appear in the filtration, right? Okay, so I don't know, who is familiar with homology, who know a little bit about homology? Oh, good, and who is not? Oh, if you, I don't know if everybody is familiar, but if you are not, don't worry, because I would say you can think about connected component in all what we are going to do. It's a bit restrictive from a practical and theoretical point of view, but the main ideas are there. So if you really don't feel comfortable with when I'm talking about homology, just think connectedness, and it should be, you will get the essential ideas. But I'm just going to tell you a few words about homology, because defining correctly, and it's not difficult to define homology. It's very simple. It can be done in a few lines, but getting the intuition may take a while because you need to think a little bit about it. And just to tell you a few, so in the course web page or in the conference web page, there is a link where you can read a small chapter that give you, we don't use a very, or at least in this course, we won't use very subtle notion of persistent homology. All what we will need is roughly summarized here. So persistent homology is a way to encode what we call cycles or holes in a topological space. So a little bit more formally, or if you are given a topological space X, a field, so we are going to always work with persistent homology with coefficient in a field. For example, it can be a finite field, like it's very usual to take Z over 2, because from a practical perspective, it has some advantages, but you can take Z over P or R, whatever you want. And a non-negative integer, that will be the dimension of homology you are interested in. In fact, you can build a vector space, which is called HK of X, which is the chaos homology group of X. And this is just a vector space whose elements represent the k-dimensional cycles in X. And the dimension of this vector space is what is called the chaos Betti number of X. And it represents the number of independent cycles of dimension k in your space. So if you really want to define this notion of holes or cycles of some given dimension, you need this kind of algebraic machinery to do it in a correct way and in a rigorous way. But the intuition is that it's a way to manage all these kind of things. Okay. And it needs a little bit of work. It's not completely intuitive, but a very well-established old standing theory. So just to give you an example, so one important property is that for k equal to 0, what you get is the connectedness. So H0 is, or beta 0, the first Betti number, beta 0, is just the number of connected components of X. Beta 1 is the number of independent one-dimensional cycles, which are cycles that turn around some kind of holes intuitively. Two-dimensional, the homology will encode the number of voids you may have. If you imagine some kind of 3D object, you may have some kind of voids inside. And you can, just to give you an example here, if you look at this domain in the plane, this is just a disk with two holes. It's beta 0, its number of connected components is 1, and it has two independent cycles, the one turning around this hole and the one turning around this other hole. So beta 1 is 2. Intuitively, it seems to be quite clear. And where homology is useful is that if you take the cycles that turn around the two holes at the same time, it can just be seen as the sum of these two cycles, right? And if we look at the example of the sphere, of the unit sphere in R3, let's say, beta 0 is 1 because it's connected. Beta 1 is 0 because you don't have, you have cycles, but they bound the disk, okay? If you take a cycle, and it does not turn around a hole. So there is no non-trivial cycle in the sphere, so beta 1 is 0. And beta 2 is 1, because you have 1-2 cycle, which is a sphere itself, because in some sense it surrounds a void. I'm just waving my hand. If you want to do this in a clean way, it would take a while, but this is just to give you the idea. And again, if you are not familiar with all this, machinery, you can think about connected component, right? H0. And another important, very important property of homology that is the following. When you have two spaces x and y, and if you have a function f from x to y, this function induces, in a canonical way, a linear map between the homology group of x and y. And in particular, something that we use a lot when we are doing TDA or persistence is that if now x is a subset of y, this inclusion can be seen as a map, a continuous map from x to y, where each point x is sent to itself. And this inclusion map induces a linear map between the homology group of x and y. Okay? And this linear map is not a trivial one in general. So, and you see here that you maybe start to see the connection with filtration that I mentioned before. When you have a growing family of spaces, topological spaces, including into each other, these inclusions induce linear map between the homology group. And in fact, what we have done before on the examples is to monitor the evolution of the homology of this family of growing spaces through this map that relates them to each other, induced by the inclusion. All right? I won't tell you much more about homology. If you have some specific question, just ask. But you don't need much more to understand the following. Okay? Okay. I just need to check the time. What? It's until 10, 15, 20 or 20? Okay, perfect. Okay, so why is persistent homology an interesting notion? We can look now at what happened if I so before we had computed the persistent homology of this function, red function, okay? And now if I perturbate a little bit my red function, I replace it by the green one here. What I can look at what happened to the persistent diagram. And as you can see in this very simple example where I changes or in the topology were due to local maximum or local maxima and local minima, right? So if I shake a little bit my function, I add a lot of new small or local minima and maxima to my function that will obviously create some new intervals. But the point is that these new intervals, in fact, are very short one. If you compute the persistence of this green function as we did before, just looking at relation of event, you will see that in fact, you will see appear some points that are new interval or points that are close to the diagonal, but that are not farther than the size of the perturbation. And the points that were here before, corresponding to kind of large interval, are still here. They are just moved a little bit. And you observe that they do not move by more than the size of the perturbation you have made, right? So in some sense, it seems that, at least on this example, if I perturbate a little bit my function, I move a little bit the point of the persistent diagram, and I possibly, if add some point, but they are close to the diagonals, I have a small persistence. When we are talking about the persistence of a point or a topological feature, we are talking about the length of its corresponding interval. And so now the question is is it a general property? How can I quantify this? So do I have some stability property for persistence with respect to perturbation of functions? And for that, we need to put a metric on the space of persistent diagram. We need a way to define the notion of proximity between persistent diagram. And there is a metric that we can put on the set of persistent diagram, which is called the bottleneck distance. There are some other notions, but this is the most natural one with perspective of stability, where you just define it as a matching distance, where what you try to do when you have two persistent diagrams, you try to match the point. So you have the green on the red persistent diagram, and you try to match the point of your two persistent diagram one by one in such a way that the largest displacement of points you make is the smallest, as small as possible, right? The problem a priori is that in general, two persistent diagrams do not have the same number of points. So for that, what you do in practice is that you allow some points to be matched to the diagonal, to be paired with some point on the diagonal arbitrarily, as you want. Okay, so here I have represented a matching which is an optimal matching. And when you have such a matching, you look at the longest displacement between one point and its corresponding point, and this is the cost of your matching, and you try to minimize this over all the possible matching. And this defines a distance on the set of persistent diagram, which is called the bottleneck distance. If you want to do it, another way to define it is just to say that you add to persistent diagram, you always add the diagonal as an infinite set, where all points in the diagonal have multiplicity, infinite multiplicity. And now, when you take two diagrams, they are both infinite with a cardinality of R. So you have many bijections between them. So you can look at when you have a bijection between two diagrams now, where you have added the diagonal, you look at the largest distance between one point and its image, and you minimize over all the possible bijection between these two diagrams. And this is the equivalent way to define the bottleneck distance. Okay? Yeah? So that's what is called the bottleneck distance. One thing that people do when they do in particular TTA, we will talk again in a moment about this notion. This is the one which is the most natural one if you want to establish some stability result. But very often you can, so this is some kind of L infinity distance between diagrams, but you can also sum up over the point of the diagram this distance to the P and take 1 over P to exponent. And this is what you will, if you look at the literature, this is usually defined as the Wasserstein distance between the diagrams. And this is one which is not very well suited to establish some theoretical result, but which is very well suited in practice because it's less sensitive to noise. We will discuss this later. Okay, is that clear, the notion of distance between persistent diagrams? And with this matching distance, we now have a first result for persistence that tells us that if we have a topological space X, if you take two functions f and g, so you can forget about the term here, tem. Let's say that these two functions are not too bad. For example, if X is a compact space and if f and g are continuous, you will be tem. So don't worry about this term. But the point is that if you take two functions defined on a topological space, when you look at the persistent diagram, they're associated to their sublevel set filtrations, the bottleneck distance between the two persistent diagrams is always upper bounded by the subnorm of the difference between f and g. Right? So if you want to perturbate the topology of the filtration of the sublevel function by more than epsilon, you need to check your function with more than epsilon in the subnorm. Yes? Sorry, could you?
Could you briefly explain why multiple systems is more stable than single variable persistent homology, or is there no theoretical?
So for the moment, we are talking about what is called multivariate persistent homology is for functions that take value not in R, but in multivariate spaces. So I didn't plan to talk about multivariate persistence. The thing, but if you want, we can discuss this, or maybe even at the discussion time this afternoon, if you have some question about this. The very important point is that this theory of persistence, say univariate or persistent homology, is very well developed from a theoretical perspective. Multivariate persistence is at the very beginning. It's much more difficult for many different reasons. And there are much less theoretical results. In particular, there is no general stability result for multivariate persistence. Does it answer your question? Okay, so that's, in fact, I guess Thomas maybe will talk about a little bit about this. I don't know, but this is in fact I'll come back very briefly on it later. But this is in fact a particular case of a much more general algebraic result. But that's in fact this result gives sense to persistent homology because this is when we compute persistent homology of a function, we get some topological information, and this is information because it's robust with respect to some kind of perturbation in the space of function. Yeah?
Let's say that, what is the general class of any functions for some complex functions?
Smooth function and compact manifolds are terms. In fact, the termness here just means that when you look at two sublevel set of your function, different sublevel set, you look at the inclusion of the first one into the second one. When you look at the homology level, this inclusion, the rank of this linear map is finite dimensional. So if you have continuous function on a compact set, there will be 10. It's not very restrictive. I'll tell a few words at the end of this morning. Okay, and maybe another interesting and important remark from the data analysis perspective is that if now you compose a function by an homomorphism at the source, you don't change the topology of the sublevel set. So the persistent diagram of a function composed by an homomorphism at the source is the same as the persistence homology of this function. So you also have some kind of robustness in this aspect that if I reparameterize here the real line, my function will be stretched or shrinked, but its persistent won't change. Persistent just see the values of the function and the topology of the level set. Okay, just now in the 5 minutes that remains, I just want to show you very briefly 2 examples as how do we use in data analysis or machine learning this kind of tools, at least persistent homology for function. One way to do it is just to say that if you have some data that comes as a function, you can compute its persistent diagram and use it as a feature to do your machine learning task. So I won't go into details, but that's something, for example, we did. This is just an example. I won't detail, but the thing is that a few years ago, we were working on the development of some tools to detect or classify some kind of arrhythmia from ECG, which are in fact one-dimensional functions. And by adding to some kind of general machine learning architecture, some part of the dedicated to the process of the persistence of the ECG, we succeeded to improve over the state of the art the detection of arrhythmia. And one of the reasons why it was improving is that the feature we got with persistent, we used a lot the fact that we add this invariance here, because there is when you look at different individuals, there is a lot of variability in the earth rate that correspond to some kind of. So when you look at the pattern of the earth rate, if you use persistence, it's not sensitive to your earth rate intuitively. So I just to illustrate a little bit how it was used. And another example, I won't have time to go into details, but feature engineering, so using persistent as a feature was, I think, was the initial way that persistent was used in TDA or machine learning. Another perspective is that persistent can also be used to improve some machine learning algorithm, not only as a feature engineering tool, but also you can try, as you are able to compute persistent topological feature or topological information, you can try to constrain some models to satisfy some topological constraint, etc. So this has given rise during the last 5-10 years to an abundant literature. There are many ideas and methods to try to do that. I just want to show you an old one that is now more than 10 years old, that you can, for example, use it to do clustering. And the idea is very simple here. So is that, so you have a data set here, this is a point cloud, it's into the plan, and you want to clusterize it. You want to split it into pieces that are in some sense consistent. So we have a finite set of points, and we are in the case where for each data point, we have a function. There is a given value at each data point. For example, it could be, if you estimate some density with your point cloud, it could be the value of the density estimate. And then you want to clusterize according to the modes or the basin of attraction of the local maxima of your density. So that's exactly what you want to, I mentioned. You want to, each cluster should be the basin of attraction of a local maxima. The problem is that when you do that, let me show you. If you do it, so the way you do it in general is that as you start from a finite point cloud, you build a graph, a neighboring graph on top of your data point, and then you can mimic the gradient on this graph, and you define you associate one cluster to each local maximum of your function on this graph, and then you look at the gradient. You simulate the gradient by saying that a point moves toward its highest nearest neighbors, and then you will clusterize your data and get as many clusters as you have local maxima on your graph. The problem is that if you do this in a naive way, this is the kind of thing you will get. You will even if your function is smooth, as you have discretized something on a graph, you will have a lot of local extrema maxima for your function, and each one will give rise to a small cluster, and you get something which is really not satisfactory. So one very simple idea to do that is to try to get help from the persistence of now the sublevel set of your function on your graph. You have a graph, which is a topological space. You have a function on the vertices, and then you can look at the sublevel set of your function that give you some subgraphs, and you look at the evolution of the homology. Here, this will be the zero homology of your graph. And that's exactly what is done here. So you start here. The color represents the value of the function, which here I use the density estimate. And when I've built a neighboring graph, I've connected the dot. Now I can look at the persistence of my function on this graph, right? Defined on this graph. And when I do that, I get a persistent diagram, which is something like this. So now it is below the diagonal because, as I told you, I use a super level set of my function, filtration. So I start from the top and I look what is above this threshold and I go down. So this gives me some diagram below the diagonal. And you see that there are different parts in my diagram. There is one, which is a set of the points that are very close to the diagonal. There is another one here, which is close to 0 with infinite persistence. And there is also a set of points that are well separated to the other ones. And in fact, here there are 6 such points. And as I'm doing zero persistence, each point is associated to a local maximum of my function. So when I'm looking at a point in the diagram here, I can look at the corresponding point in my data set corresponding to the local maximum. And for example, if I take this area here, if I look at the points here, you see that there are many points a little bit everywhere. And this can be in some sense thought as topological noise. These are the points that are close to the diagonal, and they are not really meaningful with respect to the clustering task I want to realize. Probably there are some kind of spurious local maxima. Now, if I look at the points that are in this part of the diagram, so these are points that are very low persistent. So they appear at very low value of my function f, but they have an infinite persistence when I go to minus infinity. So in fact, these points correspond to local maxima that are as they start at very low value of f, they are in low density areas. You can see them here. And they persist forever. So they correspond to some kind of small connected component of my neighboring graph that are located in the low density area. Okay, and then when I look at this part of the diagram, which is well separated to the remaining part, I'm very unlucky with this pointer. Okay, then you get 6 points here. And if you look at the corresponding maxima, you get 1 at each corner, 1 at the center here, and 1 here on this kind of annulus, right? So now there is 1 per what we would expect to be a cluster. And what we can do now is that when we know, we can read this diagram. So in some sense, we have here a gap between the topological information and topological noise. So we can fix a threshold that separates the noise from the signal, topological signals. And we can rerun our mode-seeking algorithm with a rule that whenever we meet a local maximum, so a candidate, a cluster candidate, and when the persistence of this cluster is smaller than this threshold, you define a rule to merge this small cluster or non-significant cluster into a more significant one. Okay, so you merge some spurious cluster into clusters that correspond to some real topological signal. And when you do that here, so here when you choose tau equal to 0, so you don't do anything, you get this kind of clustering. If you choose the cluster, the threshold here to be to separate these two things, you get this kind of clustering, which is much more satisfactory, right? So the point here is that from the persistent diagram, I can interpret what are the different points. If I'm able to separate some noise from the signal, I get a number of points that will give me the number of clusters I keep. So I don't need to know the number of clusters I want a priori, because the diagram will tell me. And then I can clusterize in such a way that I get exactly this number of clusters. And in fact, this algorithm comes with a few theoretical guarantees. Because of the stability of persistence, you can prove, in fact, that you have a stability on the number of clusters that you estimate, which is the stability with respect to F and to perturbation of the data. It can be written formally. It's a bit technical, but there is something. And you can also, so you don't have stability of the clusters, because it's not difficult to, if you think about it a few minutes, you will realize that there is hope. When you try to clusterize spaces according to basin of attraction of functions, you cannot expect any stability of the clusters themselves, because you can have some areas that are almost flat, and that can, just by a small perturbation, can move to one cluster to another one. You can huge. But at least you have some partial part, some part of the cluster that you can identify and that will remain stable, in the sense that you can identify for each cluster a set of points that will be always clusterized together, whatever the perturbation you make, the small perturbation you make. So this can be used, for example, to do what is called soft clustering, because in this way you can run your algorithm several times by perturbating a little bit your data. And at each time you get a point at each run of the cluster goes to one of the cluster. And at the end, you get for each data point a vector that tells you that the point is going this number of time in cluster 1, this number of time in cluster 2, etc. If you divide by the number, you get a probability for each point to belong to one or another cluster. And this allows you to identify which part where you are pretty sure about the clustering and which part are in some kind of gray zone where you don't know exactly where you fall depending on a small perturbation. Okay, I'm going to stop here just to tell you this kind of algorithm is also very simple to implement and very efficient. It's almost linear algorithm in the size of the data. And for example, it has been quite recently implemented in to solve some problem in cytometry corresponding to the first point cloud I show you, where in fact it was used to segment some blood cells in some blood samples, and it has been implemented in some software, specific software for cytometry. It's just a snapshot to show you that it's used in practice. So I think it's a good time to stop. I'm a bit late. If you have any question, we can either now or during the break.